So just a quick recall, we have this diagram for the generalized case where apparently there is slanting collision, not a head-on collision, and we established that the linear momentum of the system will be conserved under R circumstances. There will be mutual interaction between the two balls M1 and M2, and for an interaction time delta t where the things will be complex, and we established that for the system of forces etc. which are working, this particular relation we have just established that delta P1 plus P2 is equal to 0, so there is no change in P1 plus P2, it's independent of time, and that the conservation principle exists. So this conservation of momentum delta P1 plus P2 is equal to 0 is true even if the forces vary in a complex way during the time of collision delta t. I ask a question, we ask a question, why? And we answer that we don't know and we don't care. Now, in the process of collision, conservation of mechanical energy may not hold. Sometimes it may hold in certain situations. So, like the first observation is that if the kinetic energy is conserved, that is, the sum of the total kinetic energy before is equal to the sum of the total energy after, the collision is called an elastic collision, perfectly elastic collision. And if after the collision the two masses M1 and M2 which we have taken in this process, they stick together, become a single body after collision, then we say that it is completely inelastic. Mind the term, completely inelastic. And in between, when the sum of the kinetic energy in the final situation, after the collision has taken place, is less than the sum of the kinetic energies in the initial condition, then it is called inelastic, which means some energy is lost during the collision. Now we take up various cases one by one. So we take up separately as first case of the ideal situation when there is a completely inelastic collision between two bodies in one dimension. Okay. Means this body collides with this, they stick together and travel together, so that there is the concept of, at the time of collision, these two bodies come in contact and thereafter they move in this direction like this. One of the things which you have to bear in mind is that the collision is head on, and naturally when the two bodies come into contact, there is a point on the right of this body and there is another point on the left of this body, and these two bodies stick together. The angle after the collision, theta 1 is equal to 0 and theta 2 is also equal to 0. So this is an interesting situation. There is law of conservation of momentum, which when I apply it becomes m1 into v1I plus 0, because this body is at rest, and thereafter two masses they combine together, m1 plus m2, and like this. So I can write Vf in terms of Vi as m1 upon the sum of the two masses m1 plus m2 into Vi. So this is one relation that we obtain. Another thing is that we acknowledge that yes, there is a loss of kinetic energy during the collision, and this loss of kinetic energy is the kinetic energy before the collision minus the kinetic energy after the collision, which has been shown over here. Half m1 v1I square, half m1 plus m2 vf square. So I just substitute the value of vf over here and write it as m1 upon m1 plus m2 whole square into v1I square. Now look here, if I take 1 upon 2 m1 v1I square as a common factor in these two terms, then here I get a 1 and here I will get an m1 divided by m1 plus m2, which when we work out and take this in the denominator m1 plus m2 for the whole of it, so this becomes m1 plus m2 minus m1, which leaves it with m2 divided by m1 plus m2, and multiplying with this, what I get half m1 m2 upon m1 plus m2 v1I square. So this is the loss of the kinetic energy, which I am writing for us to remember as, in this case, when the two masses stick together, that is, we have a combination of two masses, then it turns out to be equal to product upon sum. Now I draw your attention to the case of to this case which you have done in your high school classes. I have two resistances and they are in parallel. Two resistances which are in parallel. Okay, I say this is R1 and this is R2. So I am drawing the parallel because the total information in physics what we have, that is similar. R1 and R2, and if you recall and you work it out, that when the potential difference is the same, then different currents they pass through them, okay, and we work out, and if this is equivalent to a single resistor, say 1 upon R, it behaves in always like a single resistor R, then we say that this single resistor R also turns out to be equal to R is equal to R1 R2 R1 R2 divided by R1 plus R2. So this is resistances in parallel. Right now I can say that the masses are in series because they stick together over here. And similarly, if I have two capacitors and we take the capacitors in series, when the two capacitors are taken in series, then those of you who are versed with that, it says that two capacitors C1 and C2 through which combine to give a single capacitor. Suppose this is one capacitor, and then in series with that there is another capacitor, and the values of the capacitance associated with them, C1 and C2, and this is equivalent to a single capacitor. It behaves as if it were a single capacitor. We say that the net capacitance of the system is equal to C. There also you get the same relation, that C is equal to C1 C2 upon C1 plus C2. Okay. Also, if there are two springs and the two springs are in series, then also one spring and the other spring, then it behaves in all prospects as if it were a single spring, then in that case also the spring constant K is equal to K1 K2 upon K1 plus K2. So I am just invoking you to look at the parallel systems which exist in physics, okay, where the spring and the capacitor, they are storage devices, resistances are power devices and power decimation devices, where they give out the heat, I square R heat, etc. So in a similar manner, when we have a combination of two masses stick together, this is probably a series combination of two masses, then the masses also, they behave in a similar fashion, and we get the relation half product upon sum Vi 1 I square. 3. So as a next item, the collision of the two masses, in the idealized form, I take up elastic collision in one dimension. Of course, the collision simple way is that the collision is head on, and the size of the two balls is the same, their center of masses are in the same plane, and of course we apply the law of conservation of momentum, that is m1 v1I, this momentum plus this momentum, which is equal to 0, is equal to v1 into v1f plus m2 into v2f. It's very simple. Now we say that the collision is elastic, and therefore there will be conservation of kinetic energy. So when the conservation of kinetic energy takes place, the elastic collision, there may not be even a sound of collision or a heat which is generated in the collision, because heat is not transformed to any other format. Okay, so I write the equation taking the lead, half m1 v1 square plus this is equal to this half m1 v1 final square plus this half m2 v2 final whole square. Or just rearranging the terms and getting away with that half, I can write it as m1 v1 I square is equal to m1 v1 f square plus m2 v2 f square, and call this equation number 2. Now if we look at these two equations, I want to eliminate one of these terms. So what I do is I multiply this equation throughout by v2f. So here m1 v1I into v2f, and here m1 v1f into v2f, and m2 into v2f whole square. The same term that we have over here. Okay, I'm sorry, over here. So what I do now is, from equation number 2, I subtract my equation number 3. And so this term here and this term here, they get eliminated. In the process, what I write is, I take m1 v1 I as common, then I have a v1I minus v2f. From this term minus this term, and here I get m1 is a common factor, v1f is also common, so here from here I get v1f minus v2f. Okay, normally the texts avoid this kind of a derivation, but the student got to stick to it, and it's easy for the text to say that it can be easily shown that. I don't subscribe to that class of people. I will, and you must not listen to them, and rather derive the equations all by yourself. So then I get this equation. So what I can write now is, I can rearrange the terms. This term V1F, V2F I can bring on this side, and I take V2F common. So I have V1F minus, here I'll get V1I, and this is equal to, here I will have V1F whole square minus V1I whole square, which of course from the formula that we have, x square minus y square is equal to x plus y into x minus y. That is very familiar formula to all of us, and we write like this. Naturally, look into these two equations, and here the term V1F minus V1I, and here also the term. So these two terms, they cancel out with each other, and what we are left with, V2F is equal to V1F plus V1I. Interesting. It is the sum of the two velocities, and of course because the velocities are in the same direction, there is no problem, we can just do that. So the second one has V1F plus V1I. Okay, so we obtain this relation. The final velocity of the body 2 is equal to the final velocity of body 1 plus the initial velocity of body 1, the first body. Now, this is the law of conservation of momentum. This equation exists as it is over here. So now what I do is, for the velocity 2f, I substitute here in this relation. And when I do so, I get this term is equal to this term plus m2, and I am writing v2f as the sum of the initial and final velocities of body 1. So I am writing it here. Now if I rearrange the terms v1i and v1i, then I find that m1 minus m2 v1i is equal to, here m1 plus m2 into v1f. I get this relation, and it looks like interesting. So I can now write the equation v1f for v1f, which will become equal to this quantity divided by this, which is presented here as the velocity of the first body after collision has taken place. Of course, it is unknown to us, so we have been able to calculate with the help of conservation of momentum and conservation of kinetic energy this relation. We find this. Now, this relation, if I substitute this value of one final velocity here, then I will write it like this: m1 minus m2 upon m1 plus m2 plus 1 into v1i, the initial velocity of body 1. And interestingly, when I rearrange the terms, then I get m1 plus m2 in the numerator, and the denominator is the same way. So what happens is that from the numerator now, not in this case, I get, instead of the term m2, so there is no m2 term here, but in the denominator it exists, and this happens to be like this, the value that we obtain, another unknown we have been able to calculate. Now I will discuss with you certain conditions in which I can apply this in various cases, special cases, where the masses are equal and one mass is greater than the other, and etc., and see as to what is going to happen. So bye bye, okay, and I discuss the cases. Okay, V2F has turned out to be this, so this is intermediate step. I have this one also gone for me, and now I take up 3 cases. In the first case, what we do is that if M1 is equal to M2, so what happens? If the 2 masses are equal, their size is equal, it's just like in the case of a billiards ball hitting head on another billiards ball. So the case is case 1. Case 1. I take M1 is equal to M2. The 2 masses are equal. Now what is going to happen? What is going to happen to the final velocity of body 1? Look here, if I substitute here, though both masses are equal, so I'll get this term as equal to 0. So ultimately this is going to be equal to, the final velocity is going to be equal to 0. And you will work it out yourself. V2F, the final velocity of the body which was hit, this will turn out to be equal to 2m1 upon m1 plus m2, that is 2m1, and this divided by this becomes equal to 1. So this is equal to V1 initial. So this is a very interesting result. What will happen is that my ball, this hits another ball with a certain velocity, the levels are the same. What will happen after the collision takes place? After the collision, this ball, this is VI1, V1I is not equal to 0, and V1F, the final, becomes equal to 0. So it comes to a stop. And for this, the V initial, V2 initial is equal to 0. But ultimately what happens is that V2 final becomes equal to V2 final becomes equal to, so V1 initial, the first body comes to a stop and the second body will move in that direction. This is true. I have been a billiards player, so this shot which I play is called a stop ball. So that my cue ball comes to a stop and the entire energy associated with the cue ball is transferred to that ball. So this is one interesting situation which we have. In the second interesting situation is that suppose one of the masses, case 2, and suppose M1 is very, very small as compared to M2. M2 is a massive ball. So what is going to happen? If M2 is very, very large, then I can calculate here that this is negligible, M1 is negligible as compared to M2, so this becomes equal to approximately minus M2 divided by M2, that becomes equal to minus 1, and the final velocity of the striking body becomes equal to the initial velocity with a minus sign. So what I am going to have is that V1 final, this becomes very approximately equal to, in practically in that situation it is called V minus V1I. And what happens to the second ball? The second ball is very massive compared to the first ball, So the final velocity associated with the second ball, you can see over here that this is m2. So this is approximately, you can say that if I divide the numerator and denominator both by m1, so this turns out to be, this will be 1, this will be 1, and this will be m2 upon m1, and m2 upon m1 is very, very large. Therefore, it's almost that it will come to a stop. It will not move. And this is where there is a third situation. And the third situation is case 3. Case 3. That instead of m1 being very, very small as compared to m2, my m1 is very, very large, a massive body which is striking the ball of mass m2. So what happens? In these limiting cases, I can see that m1 is very, very large as compared to m2. Then what happens is that this m2 is negligibly small, so it is m1 upon m1, and the final velocity of the striking body is equal to its initial velocity. The final velocity of the striking body is equal to the initial velocity. That means it will go, if you hit a ball with a bat, massive bat, Barrington's bat, and it used to be very heavy, a very famous player in my young days from England, MCC player. So what happens is that the bat will swing, and of course the collision has to be head on. Then in that case, what you find is the very interesting part is about the final velocity of the ball. m1 is very, very large as compared to m2, and therefore this I can approximate as m1. I have m1 in the numerator and also in the denominator. The two cancel out, and the velocity turns out to be equal to, how much? 2. Yani I am writing that v1 final is approximately equal to, close to, v1 initial. We'll take it as equal, and but the v2 final, the velocity of the live body or the ball which has been hit by another body head on, this turns out to be equal to 2 into vi. So never think that you have a very massive bat, you can hit the ball so that it goes and falls in Timbuktu. No, it will not. Okay, the maximum, the velocity imparted to the hit ball is twice the initial velocity of the hitting ball or bat or whatsoever. One thing I'll just share with you is, for example, I'm just giving you, just suppose I have a ball at rest, and suppose this is also a ball on the same thing, and this is released, comes here and hits this ball. So what will happen? This ball is at rest, and this comes with a certain velocity, the loss of the potential energy with the gain of the potential energy of this ball, kinetic energy, gain of the kinetic energy, it will come here, and whatever velocity it has, it will give it the momentum like this. This ball will rise in the ideal situation to the same height. This ball will stop here, and then this ball will come back and hit it back to the same position, etc. So there are very interesting questions related to, if you will ask me, I will answer. So do ask your questions, and let us together say goodbye to this chapter. Okay, I have tried to do as much as possible. There are many very interesting situations. These things you have to remember as to what is in this completely elastic collision, what is the situation, and completely inelastic system, what is the situation, and in between, of course, you must bear in mind that what is going to apply is the law of conservation of momentum. At times, we have some equations, and we have some variables. We have some knowns and we have some unknowns. You know, if I have one unknown, how many equations are required to solve it? Algebraically, 1. 2 unknowns, we need 2 equations. 3 unknowns, we need 3 equations. But sometimes there are only 3 equations and 4 unknowns. For example, in what I have just, if we have to calculate theta 1 and theta 2, interestingly, I must tell you, when you do some problems, you will find that in the collision of billiard balls, if the ball hits at the side, a sliding collision takes place, then in that case, very interestingly, theta 1 plus theta 2 is equal to 90 degrees. So, together, you must do exercises, you must, I said I will not do a formula physics, and I have not done, but I have derived the formula because most of the books I find that for the derivation of this formula, the authors have written, it can be shown very easily that V1f is equal to this and V2f is equal to this, and thereafter they discuss the cases, and you can also carry it out. Simulation exercise is called, that what if M1 is half the value of M2, 1/3 the value of M2, etc., etc. All these cases you can deal yourself and you get an insight as to what is there. That's your job. So stick to your job. Your job is learning. My job is provoking you. I hope I have provoked you. But remember, we can help each other by this motto. Thank you very much. See you soon.